My name's Darren Holmes, and today, in Chapter 6, we're going to create a reaction game. Basically, what we're going to do is program our Raspberry Pi Pico to wait a random amount of time before turning off our LED. When the LED turns off, we have to press the button, and the program will tell us what our reaction time is. So as usual, we start off by importing the machine library and importing the UTime library, and then we have to import a new library that we haven't used before, and that's for random numbers. If you look a little further ahead in the book, you can see we import machine, import UTime, and import urandom. So the next piece of code we need is to set up the pins that we're going to be using. So GPIO pin 15 is actually physical pin number 20, which we've hooked up to our LED. So that's called machine pin out. And our button is connected to GPIO 14, which is actually our physical pin number 19 on our Pico. And notice it's going to be an input, and it's going to be using the pull down resistor. So we've seen this before. One of the things we're doing here is pre-initializing a variable. So this variable is going to be called pressed, so that we know when we've pressed the button. And here we're saying it's going to be equal to false. So we can have it equal to true or false. So the next piece of code is going to take a little bit of an explanation. It's going to be a subroutine. So we're going to use the define statement. It's going to be called button handler. So this is what we're going to use whenever we press the button. So when we press the button, this chunk of code runs. Now this chunk of code is actually going to be part of an interrupt service routine. So we need to worry a little bit about what an interrupt is. We haven't used one before. So I've headed over to Wikipedia and done a search on interrupt. And you can see here in digital computers, an interrupt is sometimes referred to as a trap. It's just a request to the processor to interrupt the currently executing code. So it says the processor will suspend its current activities, save its states, so anything it was working on, it saves all that information, and then executes a function called an interrupt handler, sometimes referred to as an interrupt service routine. You'll note it says the interruption is often temporary, allowing the software to resume normal activities after the interrupt handler finishes. So if we go over to Wikipedia and do a search on interrupt handler, it says an interrupt handler, also known as an interrupt service routine, is a special block of code associated with a specific interrupt condition. So basically, this is going to be a chunk of code we set up to service an interrupt. So we're going to be using the push button to generate an interrupt. So this is going to be our interrupt service routine. You can see it's going to be a function. We're going to define it as button underscore handler. We could have called it anything we like. Notice that we're going to be passing some information to this particular function, and unfortunately they decided to call it pin. Notice it's lowercase pin, so do not confuse it with the machine library pin, which uses a capital P in there. So you notice we're going to be using it with a variable called pressed. So because we want to change the value of the variable, we're going to be using global in front of the variable just to tell it that we're going to be using the global variable pressed. In here we're saying if not pressed. So pressed can have two values, true or false. So if it is false, then it's not pressed. So we're going to say pressed is equal to true. So then we're going to print pin. Now keep in mind, pin is information that was sent to the interrupt service routine. So it's not a specific value that we can use. It's actually a group of values, and when we run the program, we'll see what those group of values is. So this is just a function that we've defined. So now we have to use it somehow. So our next chunk of code that we're going to put in is what's actually going to run. So looking up here at our interrupt service routine, that's not going to run until we call it. And we call it by generating an interrupt. So that piece of code has to be put in later. So right now what we're going to do is put in a piece of code that turns the LED on. And then we're going to do a sleep in the uTime library. And how long are we going to let it sleep for? We're going to be using a random number. It's going to be in the range of 5 to 10. So we're going to put this thing to sleep for 5 to 10 seconds, and we want it to be a random number. When it wakes up, we're going to turn our LED off. So I did a little search in MicroPython docs. I was doing a search on random, and I was looking for some information on using urandom. I couldn't find anything on urandom, but I could find something on random. So you'll notice in here there's random.uniform A, B. So this is going to return a random floating point number. So remember, floating point includes decimal places. And the number, n, is going to be greater than or equal to A. And it's going to be less than or equal to B, providing A is less than or equal to B. So looking at our code here, urandom.uniform 5, 10 is going to return a random number between 5 and 10. It could be 5.1, 5.2, 6.6, 9.9, all the way up to 10. So it's going to be somewhere between 5 and 10, so that you have to kind of wait for the light to go off before you press the button. It won't be the same waiting time every time that you run this program. So the next thing we have to do is tell it that we're going to be using interrupts. So you can see here in the book it says at the moment there's nothing watching for the button being pressed. So you need to set up an interrupt for that by typing the following line at the bottom of your program. So here we're going to have button. Now keep in mind, button is associated with machine pin 14. It's an input with a pull down resistor on it. So you can see here we're going to be triggering it from machine pin interrupt request rising. So keep in mind we have a pull down resistor on our button. So when we press the button, power goes to the machine pin. So that causes the voltage to rise from 0 up to 3.3 volts. So when it gets that trigger, or that rising value, the handler is going to be button handler. So that's that function that we just defined. So this is what our finished code is going to look like. We're going to import machine, import uTime, import urandom library. We're going to initialize the value of our variable pressed to false. The LED is going to be set up on GPIO 15. The button is on GPIO 14. We've set up our interrupt service routine. So what's going to happen is we're going to turn the LED on. We're going to go to sleep for 5 to 10 seconds. It's going to be random in nature. Then we're going to turn the LED off. And then we're going to set up our button interrupt request. So it's just going to sit there waiting for us to press the button. When we press the button, it's going to come up to the function button handler. And what it's going to do is say that pressed is equal to true, and it's going to print the value of pin. So I've entered that code into Thonny. So I want to show you what it looks like when I run it. So you'll notice that when I run it, what happens is the light goes off, I press the button, and Thonny gets this message. So notice the message says pin 14, mode equals in, pull equals pull down. So I just want to show you that that is equal to button, right? Button is machine pin 14. We have it as an input, and we have it as pull down. Now I've added an extra line of code in here. So after print pin, it's going to print button. So what I want to show you is the value in button is the same value that gets sent to our interrupt handler. So here's what happens when I press that button. It comes up and it says pin 14, mode is input, pull is pull down. And you'll notice right underneath it I said print button. It prints the identical value. So to make this game a little more exciting, we're going to change it up a little bit. We're actually going to start a timer. So what we're going to do is create a brand new variable called timer start, and it's going to be equal to utime.ticks underscore milliseconds. So this is a new function we haven't used before. It's part of the utime library. When you see the word ticks, that usually refers to clock cycles. So basically we're going to put this piece of code in right after we turn the LED off. We're going to start a timer and see how long it takes you to press the button. So we're going to delete the line in our interrupt service routine that said print pin. And what we're going to do is create a new variable called timer reaction. So this is going to be your reaction time. And it's going to be equal to utime ticks diff. So that's the difference between two numbers. And it's going to be the difference between utime.ticks underscore milliseconds, which is the current time, and the previous value that we stored when the light first originally went off. So this is going to be your reaction time. And then underneath that, we're going to print your reaction time was plus the string of timer reaction. So that's timer reaction plus milliseconds. So when you see this plus sign and you see string data, now remember string data is alphanumeric data, so it can be letters or numbers, but it's in quotes. We can only add string data to string data, so we have to use a function called str, which converts the number timer reaction to a string piece of data. That's the only way we can put it together in one long string, one after another. Keep in mind, timer reaction is equal to the difference of two times, so that's going to be a numeric value. That numeric value has to be converted to a string. So in Thonny, this is my completed code. So I'm going to run it and show you the result. So you can see here, my reaction time was 223 milliseconds. So you can see here at the start of the chapter, it says the average human reaction time is around 200 to 250 milliseconds. So in the second half of the chapter, we're going to turn our game into a two-player game. So we need to add another push button. So the push button is actually going to go to pin number 21. Now pin number 21 is GPIO 16. So in order to create this two-player game, we need to set up two buttons. So we're going to have the right button on machine pin 16. It's going to be an input, and it's also going to have a pull-down resistor on it. We're going to rename the left button as left button and keep it at pin 14. And we're going to have to change our IRQs, or our interrupt requests, so that we have one for the left button and one for the right button. Now you'll notice the handler for both the left and the right button is the button handler. So they can both use the same interrupt service subroutine because it's going to send which button got pressed to that subroutine in that little variable we labeled pin. So in the book, what they've done is they've set that code up, and you can see we have the left button, the right button, and down here we do our normal LED on, go to sleep for a random time between 5 and 10 seconds, turn the LED off, start the timer, and then wait for the right button or left button to send that interrupt request, in which case it goes up to our button handler. And what's going to happen here is it's going to say if it's not pressed, press is going to be equal to true, and then it's going to print the reaction time. Now it doesn't tell us which button that reaction time is for, so we have to add some additional code. So that additional code is a new variable, and our new variable is going to be called fastest button. Now fastest button is going to be equal to none. So this is going to be a new variable type for us. So to find out a little more information about none, I went to Google and I typed in Python variable equals none. And you can see that none is a keyword, and it's used to define a null variable or an object. So in our interrupt service routine, we're going to have to add two lines of code. The first line says that fastest button, we're going to be using the global version of fastest button, and fastest button is going to be equal to pin. So we saw the type of data that comes in for pin, so that data is going to be stuck into fastest button. So then at the bottom of our code, we're going to add two more lines that say while fastest button is none, U times sleep 1. So it's just going to keep repeating itself. So how will it ever get out of this? That's where our interrupt request lines come in. So when we press the button, it does an interrupt and gets us out of this while loop. So when it comes out of the while loop, it's going to test to see which player was the winner. So if fastest button is left button, it's going to print the left player wins. Else, if the fastest button is the right button, then the right player wins. Now we haven't seen this word is before. We could have said equal equal, but there is a slight difference between is and equal equal. So going out on the internet, I found a website called realpython.com, and they're comparing Python objects the right way, and it's is versus equal equal. It says there's a subtle difference between the Python identity operator is and the equality operator equal equal. It says your code can run fine, when you use the Python is operator to compare numbers until it suddenly doesn't. It says, however, it's crucial to keep in mind that these operators do not behave quite the same. The equal operator compares the value or equality of two objects, whereas the Python is operator checks whether the two variables point to the same object in memory. So when you look at your code and compare fastest button to left button, you'll see that left button is equal to machine pin 14, right button is equal to machine pin 16. Both are inputs and both are pull down. So when the left or right button causes an interrupt, it sends information to your interrupt handler. The handler is the same for both buttons, so the information that is sent shows up in pin. So pin is the information that's sent by these interrupt request routines. So when an interrupt is triggered, the information that is sent to the handler shows up in pin. So when we look at our code here, we can see the fastest button is equal to pin, and pin is equal to either the left button or the right button. So here we can see that left button is equal to machine pin 14 and right button is equal to machine pin 16. And we've seen from the previous examples that the information that shows up when we print pin is actually the pin number and whether it's an input or has a pull down associated with it. So those three pieces of information are actually checked. So when we say is, what we're actually doing is comparing left button and right button to fastest button. And they're both the same memory location. So what we're doing is comparing fastest button to either left button or right button, and in both cases they're both objects that are defined in our equal statements. So then the book shows you the finished code. So we're going to import the machine library, uTime library, and random number library. We're going to pre-initialize our variable pressed is equal to false. The LED is on GPIO 15. The left button is GPIO 14. The right button is GPIO 16. And the fastest button is none. This is our interrupt service routine, and it's called button handler. It's going to get some data sent to it in the pin variable. So we're going to use pressed as a global variable, meaning the value of pressed is available to us both outside the function and inside the function. So global makes the outside variable pressed available inside the function. So if it's not pressed, press is going to be equal to true, and another global variable, fastest button is going to be equal to pin, and we've seen the value of that in the first part of the chapter. Then we have our regular program. We're going to turn the LED on. We're going to go to sleep for a random time between 5 and 10 seconds. We're going to turn the LED off, and we're going to start our timer. We're going to set up the left button, interrupt request, and the right button, interrupt request. Both are going to be rising, and the handler is the button handler. So whichever one of these gets triggered first, that's going to send data into our interrupt service routine. So the rest of our program just says while fastest button equals none, or is none, we're just going to sleep. So we're just going to keep waiting until we get something put into fastest button. So you can see we have to have an interrupt, and the interrupt will go to the handler, and the handler will put pin into fastest button. So once pin has gone into fastest button, it's going to say if fastest button is left, then the left player wins. If the fastest button is right, then the right player wins. So this is my final code typed into Thonny, and as usual I'd like to use LED on rather than LED value 1, and I've used LED off. I've added some extra spacing just to line up my equal signs. And you'll notice that my code actually takes up 33 lines. I've put in some extra blank lines just to make my code a little more readable. So I'm going to go ahead and run this code and demonstrate it to you. So here I've pressed the left button, so the left player wins. I'm going to stop the run. I'm going to rerun it again. And this time I press the right button and it says right player wins. So if you go back to your MicroPython docs and do a search on IRQs, there's about 251 entries in there. So there's all kinds of different information available to you on interrupts. One of the things I wanted to point out to you is you can actually disable or enable your interrupts. So if you're doing something critical in your code and you don't want anything to interrupt it, you can actually disable them. So every so often, it doesn't hurt to stop and reflect on what code we've written in the chapters. So as a way of a little review, loops, we took two different kinds of loops. So we took the for statement, so for I in the range of 10, that was on page 27. We use the for statement when we know the number of times we want to execute a loop. In this case, we wanted to execute it 10 times. We also took a look at the while statement. So if we wanted to create an endless loop, we could use while true, and that was on page 28. Or we could do something like while username does not equal Clark Kent. So we're doing something until something happens. So that's on page 32. So for is used when you know the number of times, and while is used when you don't know the number of times you want to execute a loop. So we've just completed chapter 6 on the reaction game, and we used interrupts. I just want to take you back to chapter 5 where we used threads. So threads were basically on page 62, and we used it to monitor the button. So somebody was going to press the button, and then when we finished doing our traffic light loop, when we got back to the red light, if the button had been pressed, then we're going to extend the lights, beep the button so the person can cross the road. In the reaction game, we used interrupts, and that started on page 70. So pressing the button stops the code until the interrupt is handled. So the main differences between chapter 5 and chapter 6 is in chapter 5 we used a thread to monitor the button but don't stop your code from running. In chapter 6 we were using interrupts and we wanted to stop the code as soon as somebody pressed a button so we could declare a winner. So this concludes chapter 6 on creating a reaction game, both one player and two player. I know I make some of these videos a little more complicated than they probably need to be, but I like you to know that there is additional information out there when you get stuck. In the next chapter, we're going to create a burglar alarm. We're going to be using a PIR, or a passive infrared sensor. So please don't forget to subscribe, turn on the notifications, and we hope to see you on the next video. Thank you for watching.